Hello, it's What the Doodle, and in today's session, it is a continuation of the last video that we did, and that was about the Google file system, and it's specifically this video, and that was entitled How Does a Distributed File System Like Google GFS Works? And in that video, I did mention that sometimes the best way to learn something is to actually try and build something like that. You can get a better understanding of that. And as a consequence, I've started a new project. I don't know if I'll finish it. I will try my best, and as long as my interest carries on going on it, and I've decided to call it the RDFS, which stands for the Rust Distributed File System. So instead of, it's sort of a play on words, as you have HDFS, which is the Hadoop Distributed File System. So I decided to change the first part of it and call it Rust instead. And this is the actual project itself. Obviously, this is the just bootstrapping the project really at this stage. And as you can see, I have all this love putting a little logo, and I do reference the image in that video previously, which was a very broad overview, a very high level overview. And obviously, as I mentioned, the main thing that I do really like, or the idea that I like, is creating a polymorphic binary, so that you have a single binary, but it can work in either worker mode, master mode, or the client mode. Obviously, I'm defaulting it to be the client mode. And one thing I realized is that this polymorphic application requires the exact same state across all of them, which is it's a very nice property actually, and we can encode that globally by injecting that as environment variables, and that works really well. And obviously we have a basic usage for that, and now starting to emerge. As I said, this is very early days, and I've started to also build up a little bit of the test harness, so we can sort of jump into the actual code. Actually, let's clear that. Let's go into our code base and have a look around. So what I'll do is I'll open up VS Code when it opens up, and let's shut that down. Okay, so just to go through where we are, I mean, this is really early days, so it's just the start of it. Now, if we have a look at the main entry points, at the moment, I'm using clap in order to do a lot of the heavy lifting, and as you can see, I define essentially, clap is really brilliant, especially when you use clap derive. It allows you to create a struct and enums and whatnot, and then you can model essentially your arguments based off that. It's really nice how it all sort of works. And so essentially the idea behind, as I mentioned, is that we have it is polymorphic, and with the emphasis on it being a client CLI first. And what I've done is I've separated out each of those things. So I've got the client, if you like. This is where all of the client module, if you like. So all of the client code and all of that stuff, all related stuff, will sit under here. We've got the other two modes, which is the master mode, which obviously it's not done at the moment, and as well as the worker mode, which is, I've started to chip away at that, and I'll get into that a little bit later. And of course, a configuration, which is where we pull in those global bits of state, if you like, which are very important. And I found that global state seems to apply to whichever mode, so it works out quite nicely. We pull it in from the environment variable. And if you look at the main, as I mentioned, the polymorphic nature of it is now almost working. Well, I believe it's mostly working. None of it is actually implemented, of course, but we work sort of top down. So we work at the high level, the overall, and then we work our way through and start building each part of it. So in terms of the top level client, we want basic things like the ability to list an object or list a directory. We want to be able to get an object. We want to be able to add an object and remove an object. And finally, we have also another command. I mean, these are sub commands essentially. And one of the other things is that we can select a mode, and from the mode we can invoke either the master or the worker. So we can flip that polymorphic binary to behave either as a master node or as a worker node. So we should be able to now. Let's close this. I'll try and make this a little bit larger so you guys can see. So if I go into the well, I'm already in the repo itself. That's fine. So what we'll do is we will try and build this now and let that compile. And I'm using Axum, not that it entirely matters. I mean, there is any number of web servers that could have been used, but I picked that one because it's fairly popular. I believe it's like almost the second most popular after Actix. So as I said, it doesn't really matter so much. The main aspect is the ability to, because the worker node as well as the master node, they will essentially be like miniature little web servers. And the main reason they need that is because of the communication that they need to have, and they need to talk to each other. And so we're going to use HTTP as the sort of the transmission, if you like. The communication plane will be over HTTP. It just makes things really ridiculously simple and fairly robust, actually, based on all the other various different protocols that we could potentially use. So anyway, that has built, and I'll clear that. There's of course a lot of warnings because lots of things have not been implemented, which is expected at this stage of the project. So let me clear that now. I did mention that the state itself is required, whichever mode that you use. But we can still run that. Hopeless. Let's run this binary. If I just run the help command. So here's the help command, and as you can see, we have the subcommands. So you have RDFS, and then you run the commands, and they are, for example, list, get, add, remove, and then mode, which is the important one, where you can run this entire thing either as a worker node or a master node. So let's as an example, one of the things I did mention is that we need those environment variables, whichever mode you're in. So we have, just for testing's sake, I've created an env file, and if I cat that, you'll see. So in the env, we have these two endpoints, which is the RDFS endpoint, which is where the master essentially will be running, and a token for that as well. And so what we can do is we can actually source these. Well, actually, I'll show you how this runs. If I do cargo run, and then I do, for example, mode, and then we say we want to run the worker mode. If I do that, you'll see that it will error out because it will say, look, unable to load the valid cluster configuration. Please make sure that these endpoints or these environment variables are set. So of course, without that set, it will not run. It can't run. And this is the exact same for whether you're running as a client mode or whether you're running as a worker or a master. You'll need the same configuration. So because we have that env file already defined, what we can do is we can load that into our shell. So we can do source env. That's now loaded in, and we can prove that because we can echo, for example, RDFS underscore, let's just do endpoint. And so you can see that's actually loaded in to our environment variables. And because that is loaded in, so let's clear this out. And if we do cargo run, and we do mode worker, and now you can see we're simulating, well, it's actually launched, and it's launched in worker mode, and we can see behind the scenes whilst the actual web server is running, and it will be able to accept commands because we will be hopefully sending it, because we'll be sending it API commands over HTTP, but at the same time we want this worker to contact the master node and send heartbeats at a regular interval, and we can see that working here. And so if we, for example, if we open another tab, we can actually go to our worker node endpoint, and at the moment it's not, none of it is implemented, but we at least have this. Just proves that we have that web server is fully running. And it is fully running, and this is just almost like a bit of a hello world. It's just sort of kind of debugging it as we're going along. But if we go back here into the actual diagram, so we have that node running in worker mode and essentially sending the heartbeats, as you can see. And if we go back into the actual code a little bit, as I did mention, I'll dive into the code a little bit. So if I go into the code itself, so the actual, as I mentioned, we have the main where we have clap, which essentially we'd use clap derive to pass out all of the commands and arguments and whatnot. And based on that, we then execute, or we run different parts of the application. And that's what gives it that polymorphic nature, if you like, for that binary. And if you go into the worker part of it, so if we go into the worker, when that's initiated, what you'll see is we actually put them into different, we spawn different tasks, and we spawn the background. So this is the background service or background heartbeat here, as well as the actual Axum, the actual HTTP server. And we spawn them on two different tasks essentially. And these are the handlers, and we started to work on, which is, as we mentioned, if you go back. We essentially have get chunk, store chunk, delete chunk. Those are, if we go back into that worker node, if you imagine, as we mentioned in the previous video, at a very high level, it's very dumb. It doesn't really the worker doesn't need to have much knowledge of those chunks of those files. All it needs to do is to be able to, store a chunk when one is uploaded, delete a chunk, or retrieve a chunk. Now there is, whilst I was thinking about the architecture, there is another one that we would potentially need, and that is to send a chunk. So if you imagine, if I go back to the actual README, it'll make a little bit more sense why you would need another one, which is called send chunk. So if you imagine a worker node goes offline, and then another worker node comes along, things would have to be rebalanced, because obviously the replication factor, it would not meet the replication factor, because if you say the replication factor is, say, 3, so that chunk has to exist on 3 different separate worker nodes. If, of course, one worker node dies, then it wouldn't meet that criteria. And of course, when another worker node comes online, it would have to be copied across. So how would we do that? I think if we had another API for the worker, which is essentially to say send chunk. So what that would mean is the master would know, okay, we have a new worker, for example. So let's say worker N is a new worker that has joined, and we need to move we need to redistribute the chunks that are available on W1 and W2 to WN. Then we can send a command that says send chunk, so we can we can reference the specific chunk that we want and where to send it, and then that worker node can use the add chunk of that. So it's kind of quite nice the way that it will reuse the existing add chunk API call, but it would be kind of like by proxy. And why that is a nicer way of doing it that way. The other way would be, if we didn't have that send chunk, then it would be, from a performance perspective, a bottleneck, because, for example, it would have to call get chunk, and it would have to pull that chunk across. So it would get that chunk, and then it would do add chunk, and then the same for the W2. And you can imagine you essentially copying the data from the worker to the master, and then you're sending from the master again to the target. So that seems like that's twice, almost like, 2 legs of that journey, and that seems it seems a bit silly to do that. Essentially, it seems like an extra overhead. Whereas if we just command the worker to say, look, worker 1, you have that particular chunk, call it chunk 10 or whatever, send that chunk that you have to worker number N, and then it can do that directly. And that to me seems far more efficient, because the master, as I say, simply does the coordination. It shouldn't have to deal with the data transfers. And it would be more efficient because it can, in parallel, it could send 2 different requests. So it could tell worker 1, send chunk 10 and to worker N, and it could send another command to worker 2 and say send chunk 3 to worker N, for example. And it can do that in parallel, and that's it. These would independently then make the call to this to this target server. So that's why I believe that will be needed. Anyway, So that's where this particular project is. This is just the start of the project, of course. And as I get through and get more of it working, I will keep everybody updated. Hopefully, that's assuming that I don't lose interest in it. As with all side projects, that's what tends to happen. You get excited initially, and you have a lot of energy and momentum. But as you get into the thick of it, as it gets more and more complex, that's when the motivation starts to dip, and that's when projects get abandoned. But it would be very interesting. As I said, I really do like the idea of just seeing how all of it works. And I absolutely love the idea of having, as I mentioned, the polymorphic binary that you can just drop on a server. And one of the other aspects, obviously, I did mention I have got a test harness as well, and I'm using JavaScript. So I'm using specifically the Dino runtime in order to run. Whilst I'm building this up, I'll be needing to call some of these APIs just to trigger things and see how when I debug it, how certain things work. And in order to do that, I will need a test harness to be able to trigger certain things. And I was going to originally do it in Python, and I just thought, you know what, I've got Dino already pre-installed, and it's very easy. Just using JavaScript. The fact that it has unit test and all that built in, it's just, I know Python also has it, but it's so much low friction in terms of doing it. So it's just way easier. And using Dino tasks. So in here you can, I've set a task which is to test, just essentially call the test file. Of course, I could set all sorts of different kind of tasks, so it just saves on having to type all this out. And if you have a look, in order to execute that, assuming you have Dino installed on your machine, you can just simply, once you're inside that test harness folder, you can simply say Dino task, and then run the tasks that you want. And it's quite nice, low friction, and I do like the idea of having very few dependencies. As I say, the only thing you need for this particular project, if you wanted to hack on this as well along with me, then of course you'd need Rust installed on your machine, and optionally you'd need Dino. You don't need it really, but it does help with the testing. And yes, so that's where this is at the moment. So as I mentioned, most of the command line, of course, it's subject to change, but the actual command line part of it, the top level, if you like, is completed. The worker is now bootstrapped, and that's now running, and we do have sort of a heartbeat. Obviously I haven't implemented the heartbeat itself. Well, I can't really implement it because I need to implement the master, so it's a bit of a catch-22. But we do essentially have the ability of, essentially there are two Tokyo tasks that are spawn at the same time, and they run, the tasks run independently. And obviously the Tokyo runtime manages all of that. It's all asynchronous and whatnot. But I'll have to start implementing each of these, and I'm hoping it should be fairly easy-ish. But well, the APIs are fairly straightforward. They are essentially manipulating the chunks, and that's all the. I mean, originally they were called chunk servers. I mean, obviously in this particular project, I've called them workers, and I mean it's just a naming difference really, but they do the same thing. And as I mentioned, both having this simple API, it will also mean that when it comes to implementing the client get, list, delete, add, and remove, it will be able to contact these workers directly. And the other thing I will do is also build a sort of Docker Compose file, so that we can simulate or emulate a cluster of this distributed system, and then we can run tests on that. Of course, it won't be the same kind of performance as if we had real virtual machines running. I think that would be the next phase afterwards, but it would help to be able to just have a simple Docker Compose file that you can just do Docker Compose up, and then you can have you can simulate a small miniature distributed cluster running on your local machine as you test it. So that will be the sort of the next stages. So yeah, I think I'll keep you guys updated how once the worker node once the worker node is mostly implemented, I'll show you how that works and keep you updated, and then I'll start to try and tackle the master. Now, it will be interesting how the master is tackled, and I've got a few different ideas because the main thing, it's, as I mentioned in the previous session, in the previous video, it is a metastore database fundamentally, and I believe in the original paper, it's all stored in memory. And I mean, I can be lazy, and one of the things I was thinking of doing is just using a SQLite database. Now, I know I had mentioned SQLite database and not to use it in real projects and whatnot, and if you have highly transactional systems, not to use it. I think you can use SQLite in memory, and the reason, obviously, I've not decided yet 100%, because there is two aspects of it. There's one aspect where we need it for performance sake, where obviously we would want to store all these kind of objects and everything in memory. And then there is another aspect of it, is that we do need some level of persistence. And the reason being because, of course, once the master node process stops, as soon as it stops, everything that's in memory, it's temporary and will disappear. And of course, if the metastore database or the metastore information disappears, then your cluster is essentially dead, or all the data for your cluster is effectively dead. What I mean by effectively dead is that because that metastore, that meta information actually is almost like the index. Whilst you have all these, whilst you have all the file itself, physical files split up and distributed across all of your nodes, without having that index, you don't actually know. You cannot reconstitute that file, because it'd be very difficult, because you'd be missing that meta information about the file and how it's all tied together. So that's why we would definitely need some way of persisting that. Whilst it is important to have it in memory for the sake of performance, but we do need some sort of persistence. So to start off for the implementation, I may initially just do it as a normal SQLite database. Because I don't know what the performance is going to look like. I think for small files and a few clients, it may not be that bad, but it depends. But of course, when you scale it up to thousands, or hundreds of thousands of clients, I think there will be. I don't know what the bottlenecks would be. I think that'd be an interesting thing to do once it's built, is to do some benchmarking, is to try and understand just how many clients can connect, how many nodes can you scale this to, where does it fall off the cliff, essentially. And it's difficult to know. Again, of course, a in-memory database is going to trump anything in terms of if you have something that's disk-based, because that obviously hits the disk, and obviously that's going to be slow, and you've got network overheads as well. But anyway, all of that it's all very interesting, as I mentioned, and the only way you'll really know is by actually building this stuff and seeing how it progresses. So anyway, that is it for this particular session. And as I mentioned, hopefully as this project moves forward and progresses, I'll hopefully do more videos to cover that progress. And yep. So until the next time, I'll see you on the next one.